Sylow's first theorem, we proved it yesterday. Well, we didn't state it like this. Theorem. Sylow's first theorem. Let G be a group, be a finite group, and P be a prime number dividing the order of G. Check. Yeah. Then, if G is equal to p to the k times m, where p, where GCD Pm is 1, and what? And k belongs to n, then G has a subgroup of order p to the. Okay, we proved this last time. Okay, you remember this? This is the theorem we proved on Monday. Right here, I'm saying that P divides the order of G, so that this K here is a natural number. It's bigger than 1. Right? You have at least 1P in the prime factorization of G. Okay? Great. Now, let's do some examples. Let's do an easy example. Let's take S3. Oh, sorry. Any such subgroup is called a Sylow p-subgroup of G. Okay? So if you have a subgroup of order maximal prime power dividing G, maximal P dividing G, it's called the Sylow p-subgroup. This is the name. What is it called? Sylow p-subgroup. Okay? S3. How many elements does S3 have? 6, which is 2 times 3. Well, let's write down the elements of S3. This is the identity. I have the transposition 1, 2, 1, 3, 2, 3. And I have the 2, 3 cycles, 1, 2, 3, and 1, 3, 2. How many subgroups of order 2 I have? How many subgroups of order 2 I have in S3? Everyone? How many subgroups of order 2 I have? 3. 3 subgroups of order 2. So 1, 1, 2. 1, 1, 3. And 1, 2, 3. Those are the Sylow 2 subgroups. Are the Sylow 2 subgroups of S3. Okay?
Wait.
Why is that? What if 2 is a prime number dividing 6, and 2 is the highest power, 2 to the 1 is the highest power of 2 that divides 6. So the Sylow 2 subgroups of S3 are of size 2. 1, 2, 3. Okay? We call this a Sylow 2 subgroup, by definition. Okay, yeah?
Is the 1 supposed to be the identity?
Yeah, sorry. I had a bad calling things 1.
I mean, it's technically the 1 of the...
Yeah, I mean, usually I call it 1. What I mean is the identity. Okay? Now, what is a Sylow 3 subgroup? I have a Sylow 2 subgroup here, and then I need to have a Sylow 3 subgroup. I need to have a subgroup of order 3, at least one. What is it? Anyone can help me? Yeah, Joanna? And the 2, 3 cycles, right? So this is A3 basically. A3 the identity. 1, 2, 3, 1, 2, 3. Julian, is that what you wanted to say?
Yeah.
Yeah. Okay. Is a Sylow 3 subgroup. Easy work so far, right? I just look at the prime factorization. I determine the highest power of every prime dividing the order of G. I know I can find a subgroup of this order. I might be able to find more. I might be able to find exactly one. Here, how many Sylow 3 subgroups do you have? Everyone? How many subgroups of order 3 you have? One. How many subgroups of order 2 you have? Okay. Great. Now I'll get back to p-groups. I'll prove a theorem actually because I want to use it. I stated it last time and I said I'll leave it as an exercise. But I will do it. I think yesterday I did it in the exercise session. I proved it, so let's prove it again. Recall. Okay, so I'll use G. I should not let's see. Well, let G, I'll also use G. That's okay. I mean, you guys will not get confused. Let G be a P group. So G has order P to the K for some K and N. Of course, P is a prime number. Goes without saying P prime. P prime. Let G be a P group. P prime. And S finite G cells. Then we said that the set of fixed points, that S is congruent to the set of fixed points mod P, right? The cardinality of the set is congruent to the number of fixed point mod P, where SG is the set of singleton orbits, right? It's the union of singleton orbits. You remember this from yesterday, from Monday? Yeah, we said this on Monday. SG, we called it this way. SG is the set of fixed points. And we proved it's the union of singleton orbits, or a union of singleton orbits. Okay, let's prove this theorem. I mean, the proof is not bad. The proof is just a very quick proof. We know that S is a disjoint union of orbits. Okay, so let S1 up to Sk, say, denote what? Denote the B representatives. B representatives of singleton orbits. Of course, the case k equals 0 is obvious. If you have no singleton orbit, the case is obvious. Okay? Let S1 up to Sk be represented of singleton orbits, and Sk plus 1 up to Sn be representatives of non-singleton orbits. Okay, this is just to facilitate the proof. If you have no singleton orbits, the result is really obvious. Okay, so I can write S is a disjoint union of orbit of Si as I equal 1 to n. Then I split this union psi. Now all of these unions are disjoint, so I can take the cardinality and add the cardinalities and add them up. So this is just right plus okay. Now if these are representative of singleton orbits, what is the size of a singleton orbit? 1. So this is just k. So really, this is just Sj, so the number of singleton orbits, right? I have k singleton orbits, so my set of fixed points has k elements. Agree or not? You agree with this? How many singleton orbits you have is just the same number of fixed points, right? Look it up. Sg is a set of fixed points, or is the union of the singleton orbits. Plus some I equal k plus 1 to n g orb si. Okay? G not orb si, G stab si. What am I saying? Okay, so now what do I do? What do I know? G stab si, the index of stab si, divides G, divides the size of G. So, G stab si belongs to 1 p squared and p to the k. It belongs to this set. Now I'm saying that orb si is bigger than 1. So it cannot be 1. So it must be a power of p that is bigger than 1, right? It must be p or p squared or p cubed. We agree, everybody? Is it clear? Now, in any case, orb si will be divisible by p. So G stab si will be divisible by p for all I in k plus 1 up to n. So for all I, for all k plus 1 I n, G stab si divided by G. Great. Now, look at this equation here. Look at this equation here. Everybody, let's look at this equation. Is this divisible by p? Is this sum divisible by p?
Yes.
Yes. So when I reduce mod p, what will happen to this?
0.
0. Hence, S is congruent to Sj mod p. Okay? No? If Sj is if there are no fixed points, the result is clear. Trying to think. If there are no fixed points, the result is right. Because this would be 0 immediately. Okay? Here I'm assuming there is at least 1 in the proof. I'm saying S1 up to Sk, just to facilitate the proof, but it isn't much different. Okay? Are we good here? Great. Now, oh, I erased it, but that's okay. We'll move on to Sylow's second theorem. But let's now define what two conjugate subgroups are. Yes? What is the order of G? This is just G stab SI times the order of stab SI. Okay? Okay. Now, another definition. Let G be a group and an H a subgroup of G. A subgroup K of G is said to be conjugate to H if there exists G and G such that GK G inverse is equal to H. Okay? This is a definition. We say that two subgroups are conjugate if G, for some G and G, GK G inverse is equal to H. Of course, you can check that conjugacy on the set of subgroups is an equivalence relations. A subgroup is always conjugate to itself. Why is that? Pick the identity. E.g. K, E.g. inverse is K, right? Now, if GK G inverse is equal to H, then conjugate by multiply by G inverse here and G there, you get that H is conjugate to K, and transitivity works the same way. Okay, so I'll write this down. Conjugacy is an equivalence relation on the set of subgroups of G. Now you can check this. I mean, it's not bad. Or you can anyway. I mean, okay. Great. Now let me give a small. Let me talk about this conjugation business in a more detailed manner. Proposition. Let G be a group. And let G be in G. Let phi sub G be the function defined from G to G that sends X to G X G inverse. Okay, so I fix G and I send everything to G X G. I send X to G X G inverse. I have a fixed G. I let my X vary and I fix G. Okay? Phi G is an isomorphism from G to G. Do I need to do that or you can check this? Can you guys check this or should I do it? Should I do it?
Yeah.
I mean, okay, let's do it. Proof. Let x1, x2 be in G. What is phi G x1, x2? This is just G x1, x2 G inverse. I mean, we can say it's a bijection because it's, anyways, using group action we can say it's a bijection. But anyways, let's not do that. So what is that? This is just G x1 G inverse G. Just multiply by G inverse G in the middle, you can do that. G inverse. This is just Gx1 G inverse. And Gx2 G inverse. So just phi G of x1, phi G of x2, which is a homomorphism. So phi G is homomorphism. Homomorphism. Okay, now, how do I show it's bijective? I can show it's bijective, I can show it's injective and surjective, or I can find an inverse for it. What's a good candidate for the inverse of phi G? Phi? What's
inverse?
phi G inverse, right? Phi G inverse composes phi G and x. What is that? This is just G inverse phi G of x, G. This is just G inverse Gx, G inverse G. Duck, this is just x. Similarly, by flipping the roles of G inverse of Rho, phi G composed with phi G inverse of x is equal to x. Hence, phi G inverse is the inverse of phi G, and well, hence phi G is bijective. And hence isomorphism. Therefore, corollary, any two subgroups of G, any two conjugates subgroups of G are isomorphic. Why is that? So let H and K be conjugate. Let H and K be conjugate subgroups of G. Okay, so what can I say about H and K? How can I write K? Then, for some G and G, K is equal to G HG inverse, which is just phi G of H. Right? And this phi G is an isomorphism. Phi G is an isomorphism. So phi G, so H is isomorphic G H G inverse G G. Okay. Great. Enough time on clarification. All of that to prove Sylow's second theorem. Sorry, it's a bit fast. This should be more or less. You should be comfortable with this by now. Okay. Okay, now we'll go a bit slower to prove Sylow's second theorem. Sylow's second theorem. Let G be a finite group. This is a strong theorem, very strong theorem. Let G be a finite group, and P a prime dividing G, dividing the size of G. Write G as I use the M after I use the M, right? P to the k times M. Is that what I used? Yeah. P to the k times M, where k is in N, and sorry, I'm just writing fast here because this is the this is not really the statement. This is just the assumptions, which are almost the same, which are the same. Then, if K and P are two Sylow p subgroups of G, then K is conjugate. Very strong statement. So if you have a group of order 24 and 24, can you factor it? How can you factor 24? No, the primes. 2 cubed plus 3. So in a group of order 24, the Sylow 2 subgroups, what are the size of the Sylow 2 subgroups? 8. Okay? We agree? What's the maximal power of 2 that divides 24? 3. So 2 to the cube. So the Sylow 2 subgroups have size 2 cubed, which is? Everybody? 8. Now, any two subgroups of order 8 in S4 must be conjugate. This is such a strong statement. This is not true if you take two subgroups of order 2, for example. If you take this subgroup and this subgroup, they have order 2, but they're not conjugate because these two elements don't have the same cycle shape. So it's a strong statement. And the proof of this strong statement is like 2-3 lines. Let's prove this. This is a very good proof. Proof. Okay. How are we going to prove this? Elegant proofs come from where usually? Group actions. Right? So, define the following. Obviously, this is an action of K on G modulo P. So I have the cosets of P. I usually let G act on them, right? G on G mod P. But I can restrict my elements of G to being K, because K is a subgroup of G. So you take K in K, star XP, you get KXP. Right? This is the action. Usually I let G act on G mod P. G star XP is GXP. Now I can restrict my coefficients to being, my elements here to being K. There's nothing wrong with that, is there? This is well defined. I mean, this is a product in G. Right? I can do that. This is called the restriction of the action of G to K. Okay? Is this clear? Is this clear? Is this clear? So you can let G act on G mod P, and you can let any subgroup of G act on G mod P. There's nothing wrong with that. Great. Now what is the size of K? Oh shoot, I can't use K. Let's use Y because I use K upstairs, right? Y, X, and let's say here Y belongs to K, and X is in G. Right, I use K here. Now what is the size of K? K is a Sylow P subgroup. So what is the size of big K? What is the size of big K? P to the K. So K is a P group. Agreed? Yes?
How do we know that that's the size of K?
Sylow P subgroups. Okay? If they're Sylow P subgroups, their order is the maximal power of P that divides G. What is the maximal power of P that divides G? Clear? Okay. Now, what can I say about this action? What is G mod? What is the size of G mod P?
the size of P, which is just n.
n. G mod P is n. Agree with this or not? P has size P to the k. G has size P to the k times m. What is the size of this? How many left cosets do you have? M. Agree so far? Great. I claim that this action has a fixed point. Can I use the previous theorem I proved on the number of fixed points? Look at the previous theorem. I'm saying if I have a P group acting on a set, then the size of the set is congruent to the size, to the number of fixed point mod P. So let M, let's say, I don't want to use N, let N. Well, yeah, I could use it. Be the number of fixed points of this action. Then the size of G mod P is congruent to N mod P. Look at the previous theorem. M G mod P is congruent to N mod P. Now, what is the GCD of, so this is M, this is M. Now, is G mod P congruent to 0 mod P or not? So look at, is M divisible by P?
No.
M is not divisible by P. Where's that? M is not divisible by P. So N is not congruent to 0 mod P. Agree? Since P does not divide, since GCD PM is 1. Agree or not? Agree? Everybody? We're good? Now, if n is not congruent to 0 mod P, can n be 0? No. Hence n is not 0. Hence n is different than 0. And n is at least 1. Well, what can I then say? Hence, this action has a fixed point. Agree or not? Yes, everyone? Are we following? Yes? Yeah, you guys should ask. Ask. Yes?
Wait, how does it imply that that has a fixed point? I don't understand.
That n has a fixed point?
Yeah.
So you agree with here? Up to here you agree? Good so far? Now if n is not congruent to 0 mod P, can n be equal to 0? No. So if n is not equal to 0, it means that n is bigger or equal to 1. And n is the number of fixed points.
Oh,
Okay?
okay.
Yes?
So you have that n mod p, and then you have GCD of p n is equal to 1. But how do you translate this something with n to something like n?
Great.
GCD of p and n is equal to 1.
Sure. Awesome. GCD of P and n is equal to 1. Can n be equal to 0?
Oh, okay.
Yeah? All of these statements are the same. Very good. So what is your friend is saying that if n is congruent to m mod P and GCD of P m is 1, then GCD of P and n is 1. Can n be equal to 0 then? No. So n is at least 1. Very good. Very, very good observation. Yeah. Yeah.
So why is, if you let n be the number of fixed points, why is the order of G mod P equal to n mod P?
Previous theorem. Okay? That if you have a P group acting on a set, the number of fixed points is congruent to the size of the set mod P. Okay. Now let what? Let xp, say let x0 be this that be a fixed point. And if I have a fixed point, it means that the orbit of x0p is equal to what? To x0p, right? This is what a fixed points mean. That its orbits, it's itself. Its orbit is itself. What does it mean? Hence, for all k, for all let's see, y in k, y star x0p is equal to x0p. This is by definition of my action. This is what means the orbit to be a singleton. Y star x0p is equal to x0p. Well, this is just y x0p is equal to x0p. Bring back the x0 on the other side. Becomes an inverse. So for all y in k, so for all y in k, x0 inverse y x0 belongs to p. Agree with this? This has nothing to do with group actions. Yes, sir.
Is it like wait, I have some fundamental question. We already used y as a variable, like at the start of the
Yeah, I mean,
it's the same.
yeah,
Okay.
yeah, for all y in k, I use it to indicate an element of k, right?
Alright.
So for all y in k, y star x0p is equal to x0p. This is what's meant to be a fixed point. Now the definition of my star is y x0p is equal to x0p. Then bring the x0 on the other side by multiplying by x0 inverse, so you get an x0 inverse y x0p is equal to p. This has nothing to do with group actions. So x0 inverse y x0 belongs to p. Yes, sir?
But then we did it for P, but we could do it for K, and then we show that.
Yeah, very good. Very good. Exactly. Well, so y belongs to x0, what am I going to say? x0, x0 b x0 inverse. So k is congruent to x0. So k is contained in x0p x0 inverse. We agree? Follow the steps. Y belongs to x0p x0 inverse. And y is an arbitrary element of k. So k is contained in x0p x0 inverse. Yes?
So we're just allowed to, like, whenever we have an existence, like an element exists in P, we're allowed to just, like, multiply.
Yeah, exactly. Yeah, you're allowed to multiply. Yeah. What does now? So k is contained in x0p x0 inverse. Now, what are the sizes of these two things? Now, the size of k is equal p to the k. And the size of x0p x0 inverse is also equal p to the k, right? Because it's a conjugate of p0, which is equal to p to the k. Now, k is a subset of this set. These two sets are finite, and they have the same size. So what can I say about them? They're the same. Boom. Or, as your friend said, you can reverse the order of k and p. Okay? Yeah, but here they're finite, so you don't need to do that. Okay. Very good argument, very fast, very quick.
It was quite a few lines, and that is a very creative decision to make.
This is a very
creative decision to make.
Yeah, I mean it's so in the book they do a longer proof. I decided not to look at the proofs of the book. Okay? So the proof of the book is normalizers and I don't know what. So we can safely ignore this. And we can just now prove the third Sylow theorem. Yeah?
Can you just clarify why x0 px inverse, px0 inverse is the same size as p?
Very good question. conjugation by x0 is an isomorphism. Look at the previous, just the previous page. Is an isomorphism, right? Okay, so these two groups, this is the image of P under conjugation. So they have the same size. Okay, now we have 10 minutes. We can prove the third Sylow theorem. And then move on to applications tomorrow. Okay, this stuff is, you should just read them. Okay, just read and redo the proof. Yes?
Why exactly is x inverse y x in P?
Oh, multiply by x0 on both sides. By x0 on this side, x0 inverse on this side. Make sense?
But then y is y.
What? So multiply by x0 on this side. You multiply, you get x0 here. This goes away. Multiply by x0 inverse on this side. This goes away. You have an x0 inverse here. Is that clear? Okay, Sylow's third theorem. Algebra finite group. G is equal to p to the k times m, where k is in n, GCD, mp is 1, and p is a prime, of course, p prime. Then, the number np of Sylow p-subgroups satisfies the following. np is congruent to 1 mod p and np divides m. So not only can you say that that such a subgroup exists and any two subgroups are conjugate, you can limit the number of Sylow p subgroups by this thing. Now I'll prove one. And we'll discuss the consequences tomorrow. Proof. Now, in the homework, you proved that G acts on the set of conjugates of H in question 2, right?
Yeah.
You remember this? Did we do the bonus homework?
On homework 7.
The bonus one. One of the question 2. One part of question 2.
S equals to x, h.
Exactly. So you have seen that G acts on the sets of conjugates of H, right? Did you guys do this question or not? Did you do the bonus?
I did.
ChatGPT? Yeah. ChatGPT?
Yeah, it's not reliable for that.
Yeah, I know it's not true. Sometimes it makes mistake on this. Anyways, so we're gonna use this action. So let P be a Sylow be subgroup of G. So I mean, I said yesterday, if I'm gonna give you a problem on Sylow subgroups, a big problem on Sylow subgroups, I will break it into steps. Okay, I will not give you something really difficult. Okay, I will break it into steps as usual. Okay, so let P be a Sylow P subgroup of G. And consider the set S xp x inverse as x is in G. Note by Sylow theorem 2, Sylow second theorem. S consists of all Sylow p subgroups, right? Because all of them are conjugate to each other. S is the set of all subgroups. I'll just take 2 more minutes, sorry about that, of size p to the k. Now, how much time do I have left?
5 minutes.
5 minutes. Okay, I can do that. Let P act on S. So now I don't want G to act on S. I want P to act on S by the following action. The regular action that you've seen in the homework. So you take Y, P cross S to S. Y, what? And you say X, P, X inverse. And you get Y, X. This is you've seen in the homework. This action you've seen in the homework, no?
Yes.
Okay. Now what can I say about the orbit of P? Now P belongs to S clearly. The Sylow, if you put X equal to the identity, if X is equal to e.g. XP X inverse is equal to P, right? I mean P is a P Sylow. So P belongs to S clearly. Now if Y belongs to P, what can I say about Y, P, Y inverse?
It's equal to P.
Everybody?
It's equal to P.
Others? Are we good? If Y belongs to P, Y, P, Y inverse is equal to?
P.
Are we good with this? Multiply P with any element of P, you get P. And then multiply by any element of P on the right, you get P. Right? P. So P is a fixed point. P in S is a fixed point on this action. So far so good. Now I claim that P is the only fixed point of this action. You have no other fixed points. Now let's recall something. Okay. So okay. So suppose P prime is a fixed point on this action. Then Y star P prime is equal to P prime for all Y and P. Hence, Y P prime Y inverse is equal to P prime for all Y and P. Agree? Now, if hence, for any Y in P, I'll write it this way. YP prime is equal to P prime Y. Therefore, Y belongs to the normalizer of G of P prime, which is the set X and G, G and G, such that GP prime is equal to P prime G. Yes, sir.
Is P prime like in S as well?
Yeah.
So like
Exactly.
It's not like a specific point.
No, I'm saying suppose it's a conjugate. Suppose is a fixed point. Suppose p prime in S is a fixed point. Now, if p prime is a fixed point, then y p prime y inverse is equal to p prime by definition. Hence, for any y in p, y p prime will be equal to p prime y, right? So y will belong to this set we defined, the normalizer. Yes, sir.
But this is the same thing as the central.
No, this is as a subgroup. You need the cosets to be equal, not necessarily every point to be equal. Okay? Is that clear? Yeah? Is it clear? Okay.
The normalizer.
Recall that ngp prime is the normalizer of p prime and g, and we proved in the homework p prime is a subgroup of ngp. Homework 7. And the normalizer is a subgroup, right? We proved this in the homework, right? Yes? ngp prime is a subgroup of G. Okay. Great. So we'll continue with this next time. I will. Then the argument is very short. Okay. Great. So see you all next time.